Welcome everyone, my name is Dora Babic and I will present our research, a continuous time implementation of pooling. The pooling operation can be separated into two distinct functionalities. First, the selection of the largest activation in a neighborhood which ensures invariance. Second, dimension reduction by keeping only the largest activations in neighborhood. We see the parameter of the second step, the number and position of the kept elements, as an architectural parameter, which determines the size of the feature maps for the next layer. Meanwhile, the selection range can be determined independently from this. In typical maximum pooling operations, the two functionalities are handled simultaneously. For example, 2 by 2 windows are determined, and in these, the largest activations are selected. In this other example, the two operations are separated. The maximal activation value is selected first in a 3 by 3 window centered around the values, and later from this map, the largest activation values with a stride of 2 are selected, just like in the first case. As it can be seen from these examples, the two operations provide drastically different results. The subsampling size is an architectural parameter which is determined by the selected network architecture, but the receptive field of max selection could be optimized. Unfortunately, it is also a hyperparameter. Wouldn't it be great if we could have pooling sizes of 2.5, for example? The lack of invariance in CNNs was demonstrated in the paper, making convolutional network shift invariant again. In the paper, they proposed a solution where a fixed anti-aliasing filter is applied, which increases the invariance of the network, but keeps the pooling parameters as hyperparameters with the additional filter parameters. To demonstrate the caveats of maximum pooling, we have created a simple simulation in which images with only two high-intensity pixels were generated, and the network, we have selected LRAT5, had to estimate the distance between these pixels as a regression problem. The original architecture could not solve this problem since it depends heavily on the receptive size of the network. We have also created a modified version of this experiment and generated images where the distance between the higher intensity pixels was less than 7 pixels. Even in this case, the average squared error was around 4. This is caused by the fact that max pooling is completely insensitive to the position of the highest intensity in the pooling window. To fix these problems, we introduce our method, continuous time pooling. The motivation of our method comes from differential equations, such as heat diffusion, but large values spread out on activation maps in a continuous way. One can easily see that this operation also works the same way as a traditional maximum selection, but here the window size depends on the execution time of the diffusion operator, and this execution time is a floating point parameter. Also S, which determines the strength or speed of the diffusion, is another floating point parameter. On the videos, one can compare how maximum pooling and continuous diffusion selects the largest intensities in neighborhoods. In the bottom, one can see the result of Dirac delta activations after the pooling operator with different pooling strengths. As it depicted, different S generates different window sizes, where in the middle white region the operation is location insensitive, and at the borders, yellow to white regions, the activations are slightly decreased. Unfortunately, differential equations cannot be efficiently executed on GPUs, and because of this, we have approximated our equation using the Euler method. This way, we have a number of iterations, which is an integer number, but the window shape is determined by H and S, which are floating point numbers. Therefore, they can be optimized using gradient-based methods. We have tested our implementation on the previously described setup, where only the pooling operations were changed, and then it can be seen it has significantly decreased the error of the network. The red curves plot the error for continuous pooling, meanwhile the blue depicts the result with traditional max pooling. We have also checked how it affects the performance on the various datasets and architectures and compared it to maximum, local importance-based, and wavelet pooling. Continuous pooling resulted in not significant but consistent improvements in most cases. We have also compared the pooling operations on the MS-COCO dataset with Mascar CNN network using GresNext 101 backbone, and here the result can be seen for segmentation. Also for detection, as it can be seen, continuous pooling provided increased overall accuracy for both problems. We have demonstrated a novel pooling method which substitutes the discrete maximum pooling with a continuous variant. Because of this, with the floating point parameters of our method, the receptive field can be optimized using gradient-based methods. This results in higher accuracies on various tasks, architectures, and datasets. For more detail, please read our paper. Thank you for your attention.